Okay, let's talk about some more bonding and some more solid types and solid things. So in metals, we know that they conduct electricity, heat, they're malleable and ductile. And the modeling we have for it helps explain that. The simple model we learned um, in introductory chemistry is called the electron sea model, which essentially tells us the electrons just float around in a space around the metal cations in a sea of electrons. And it's fanciful and it makes sense and it explains everything quite well. It's a good model. But a more advanced and more appropriate model is called the band model. We've already introduced this idea when discussing conduction earlier. Electrons are assumed to travel around a metal crystal in molecular orbitals formed by valence atomic orbitals of the metal ions. Molecular orbitals, as a result, are very closely spaced in energy levels. This is unique to metals here. Thus, they are a continuous band. Some molecular orbitals are empty. Mobile electrons are excited into these empty molecular orbitals, and the electrons are then free to move throughout the metal crystal. So here's that image again of the empty molecular orbitals compared to the filled molecular orbitals. Um, what we're looking for is to understand that there's very little gap here. In other words, the electrons in the molecular orbitals, the valence electrons, are able to easily slip into this conductive band of a molecular orbital right above it. Okay, so the band model, being part of molecular orbital model, um, does a better job of giving a little bit more order to where the electrons are. Okay. What are alloys? Alloys are mixtures of metals. And there's two types to know: substitutional alloys. Alloys of about the same size, replacing atoms from the pure metal. Um, then interstitial alloys are smaller atoms that fill in spaces between the larger metal atoms. That would be like high carbon steel contains carbon atoms in between the atoms of iron and helps strengthen the metal. Whereas the substitutional alloy changes some of the properties of the metal, making it favorably do something or look a certain way. Um, so again, covalent network solids and network atomic solids. Um, we see atomic solids with strong directional covalent bonds. They're brittle and they don't conduct electricity very well, like carbon or silicon. And we talked about the different allotropes of, carbon atoms. So again, with the different allotropes of carbon, this is the strongest type of solid. Okay. Um, this is a better image, or a larger image of the 3D nature of carbon and diamond. And you see that you have tetrahedra that are bound to each other in 3 dimensions. And these are all covalent bonds. There's no IMFs doing any of this. These are all sp3 hybridized as well. You see each has steric number of 4, or has 4 electron domains around it. Graphite has layers of 6-member rings, and they're sp2 hybridized. So what you don't really see in the diagram here is that there are pi orbitals in the overlapping, and there's no double bonds, but the pi orbitals are overlapping, and that's where the electron conduction comes from in graphite. You might see people use graphite to complete circuits in different circumstances. Um, you can convert graphite to diamond at very large pressures and temperatures. This is an example of MOs in a diamond versus a typical metal. Diamond's a great insulator, and the reason is this large energy gap between the filled molecular orbitals and empty molecular orbitals in diamond, whereas in a metal you have very little gap at all. And again, this is a molecular orbital theory, and this is a physical gap that electrons would have to gain this much energy in order to be in the conduction band, where electrons could travel in the space around the molecule. In metals, it's a much smaller gap, and therefore it explains the conductivity of metals better than diamonds. Silicon-based compounds, and this is a fun quote, are to geology as carbon is to biology. Most important silicon compounds contain silicon or silicates, and there's lots of different types of silicates. let's look at some diagramming. This is just kind of neato. Very similar to diamond structure. We have tetrahedra that form from the silicon dioxide, okay? And then you see the silicon, the various types of silicates that form as base units that form all the different types of rocks in geology based in silicon. Semiconductors are elemental silicon is the same structure as diamond, but the energy gap between filled and MOs is smaller. Thus, few electrons can cross the gap at room temperature, making silicon a semiconductor. So that energy gap in band theory that we were talking about is smaller for silicon than it is for carbon. At higher temperatures, where more energy is available to excite electrons into the conduction bands, the conductivity of silicon increases. Most metals have decreased conductivity at higher temperatures. This is why silicon is so special in computers. It also doesn't have some undesirable properties of metal that we know that help metal age well. Or poorly, pardon me, help metal age poorly. You can use a process called doping to alter the conductivity of a silicon sheet or a silicon object. Doping is a process that increases the conductivity of silicon. Very few of the silicon atoms are replaced by other atoms such as arsenic. Arsenic has one more valence electron than carbon does. This gives more electrons for conduction and produces what's called an N-type semiconductor, and the N stands for negative. So when arsenic's present, there are more electrons than usual for conduction, and it produces more electricity by making it more negatively charged. If you instead replace silicon atoms with something with fewer electrons like boron, we produce what can be perceived as a hole where their electrons can go, a place for electrons to travel through. And what that does is it allows electrons to then follow the path and sort of produces a chain effect. And this is a p-type or a positive semiconductor. So those are the two types, and there's illustrations there. So the types of questions you can expect from this are going to involve how would you expect this to behave, or what type of semiconductor is it. When the atom has more electrons, for example, arsenic has 5 rather than 4, you're going to have more negative charge on the silicon sheet. Therefore, you have an N-type semiconductor, and the opposite is true for boron. So here we go with filled molecular orbitals, excess electrons to jump into the conduction band for an N-type, and then for a P-type, electron vacancies due to doping here allow electrons to move through and conduct a little bit better in that method. On that note, I'm going to switch and go to a slide that I'm going to actually give you in class in different form that summarizes the types of solids and what they're made from, describing the bonding type, and then some properties. It's a very useful collection of all the little ideas we've talked about in terms of solids, and you'll get that in class. And on that note, we'll see you on the next video.